Okay, so let's continue with a carbocation. So again, in summary, for carbocations, the stability for carbocations is that it's more stable with 3-degree carbocation than 2-degree, than 1-degree, and methyl, just simply methyl carbocation like this one. And of course, do not forget to remember the factors that could stabilize your carbocations. Yes? Yes.
Di-share. Ay, wala yung nakita nga. Di-share mo.
Ayun ako na-share. Sure. How about this? Can you see?
Okay na, ma'am.
Okay, so remember on the factors that could stabilize your carbocation. First one is hyperconjugation. Whenever you see an sp3 hybrid orbitals like this one, it's also possible already to have hyperconjugation because sp3 and unvacant p orbitals of your carbocation can do partial sideways overlap, similar to a pp sideways overlap of a double bond. So that's hyperconjugation. Second factor again is the electron donating inductive effects. So you can utilize the electron donating inductive effects whenever you have alkyl groups, usually alkyl groups. So it can induce to disperse a positive charge like this one. So more or less, more similar ang trend, no, with electron inducing inductive effects. More similar, but the mechanism is different. So whenever you see in alkyl groups, it can induce the positive center of your carbocation by donating from its electron density. And third, of course, is the resonance. So resonance, where you can find that whenever the carbocation has a neighboring carbon double bond, can undergo, it can stabilize, no, because it can be involved with a delocalization, pi electron delocalization with our resonance forms. And I hope in the future we can encounter with that one. Okay, so, and for the hyperconjugation video, let's see if we can watch this, or you can watch by yourself now. So let's watch a video if it wasn't clear with you what hyperconjugation is. I'm just looking for the, I am looking for orbital, this one. Okay, so you see this one, there is an sp3. This is your carbocation with the p orbital, vacant p orbital, and then you have a neighboring atom with an sp3 hybrid orbital that's bonded to, let's say, hydrogen here, CH3 bonded to hydrogen. So you have that one, and they could undergo sideway orbital. Let's see. Okay, so there is an electron density. Of course, here there's an electrons shared between carbon here and hydrogen, for instance, sp3 carbon. So it will sideways overlap with that, and therefore it can share electrons here, and that's how your carbocation can be stabilized. Okay, so let's go back to our slides. We have already discussed this. So let's go for the stereochemistry of the SN1 reaction. So let's see, the stereochemistry would have, since what is this? Is your carbocation here. So once you form your carbocation with an SN1 mechanism, no, so your nucleophile can attack front or back. And because of that, you can form two types of stereo products, no? So if one can be R, the other can be S. And it's what we call as the process of forming an optically active compound into a racemic form is what we call as racemization. No, so if the original compound loses all its optical activity in the course of the reaction, so we call this one as complete racemization. But if there's only if the product or the reactant is converted only to a racemic form, partially converted to a racemic form, that we call as partial racemization. So in racemization, remember the racemeric form. When you have an equal amount of your S and R in the mixture, in the solution, even if the original substance can rotate the plane polarized light, like say here, it can rotate, let's say, counterclockwise, and the other can rotate clockwise, no, in the same degree, and they are present in the same amount, 50-50%, then the overall solution wouldn't be able to rotate the plane polarized light. So it becomes optically inactive or racemic form. And this is the one of the concerns when the SN1 mechanism is followed or utilized. No? We actually produce a product that is in racemic forms. No? So one will retain the activity like S from the initial reactant, and the product can have S, but it can also produce the another configuration of the product. Let's say another product could be the R4. So the SN1 reaction proceeds through the formation of an intermediate carbocation, and because of its trigonal carbocation, of course it's a chiral, it can react with water at equal rates from either sides to form two different stereo products, stereoorganic products. Okay. So if we go back again to the mechanism, again, the reason for racemization, formation of different stereochemistries because of the formation of the carbocation. Whenever in the step reaction mechanism, we produce the carbocation, then of course our nucleophile can attack up and below the plane of the carbocation. Okay, so if it can attack, for example, this water here, you will produce oxonium rather, alcohol with the hydrogen here. Okay, let's go here first. Step 2. Okay, so water will react to the carbocation to form a bond, or below can form this one. And of course, when it attacks up and below, the stereochemistry of the product would be different. And so you have here, this is below and this is up. So if the proportion of the two reactions are in equal amounts, then you have a racemic mixture. Question, keep in mind that carbocations have a trigonal plane. Write the structure for the carbocation intermediate. Write the structure for the alcohol or alcohol you would expect from the reaction of iodyl cyclohexane in water. So if, for example, the substitution reaction of iodide with water occurs in the SN1 mechanism, then write the structure of the carbocation. You can write the structure and write the structures for the alcohol. You can answer this by yourself. You can have your OH, dire, or dire-2A, and of course, just have your carbocation. Sometimes in the reaction, your reactant can also be your solvent. So in that case, you have what we call a solvolysis reaction. So in a solvolysis reaction, again, it's a nucleophilic substitution in which the nucleophile is a molecule of the solvent. The solvent, which is cleavage by the solvent. Example is the hydrolysis. So in hydrolysis, for example, bromine here is substituted with OH by the reaction of water. Okay, I can hear some background. If you can mute yourself. Sa mana. Sa Arniel, wala makamute. Makamute, more mute. Okay. So here you have your water acting as your nucleophile, then you call this one as a hydrolysis. No, the solvent is also the nucleophile. Again, in this case, water. Or you can have methanolysis. The solvent is alcohol, such as methanol, and it's also a nucleophile, and it will replace the chlorine here with OCH3. Okay, so this is an example of a sulfolysis reaction. Naghang akong computer. Okay, next. What product would you expect from the following sulfolysis? So sulfolysis here, H3OBr. Of course, the first step, again, para dili mo maglibog, no, you always have to form your carbocation first. So have your bromine leave your substrate, and you will have your product. In this case, you have your cyclic ring here. Of course, you have your ring and your CH3 plus positive on this carbon. So you can attack your methanol. Emphasize the lone pair. Now, whenever you show the reaction, do not just write CH3OH. Now, whenever you are asked to have the product para dali ra mo ka-predict, you always have to emphasize the lone pair. So O, emphasize the oxygen, the nucleophile with its lone pair. Para you can easily predict and see where do the electrons go and what happens to the atoms. So for example, you have your methanol here with the lone pair. It will attack the carbocation. Of course, you form a bond here. Duha pa nakaband kang oxygen, no, with some methanol. So when it utilizes the lone pair, it forms a bond here. So oxygen now will have 3 bonds plus a lone pair. But of course, since it is a 3 bond, it becomes positively charged, right? And of course, we don't want our alcohol. Alcohol is not positively charged. So it's not stable for an alcohol to be positively charged. So we use another molecule of our solvent to eliminate the proton here. Now, of course, between oxygen and hydrogen, hydrogen will be the most positive. Na naman, the oxygen is an electronegative atom, maski pa og positive charge siya because it will draw the electron density from hydrogen and carbon here, no? And between carbon and hydrogen, hydrogen is the most exposed, no? Wala siya babag, no? There's no other atoms that protects this hydrogen. So it's the most exposed, it's most positive, so therefore our nucleophile can easily abstract this hydrogen here to form a bond. So pag i-abstract ni, we use the electron pair, paingon ng hydrogen, the electron pair, kang oxygen and hydrogen will go to the oxygen, balik. So you will have O dot dot and CH3, and you will have O CH3 hydrogen plus another hydrogen, then you will have a positive one. So you have your CH3 OH. Okay, it's protonated. Okay, so that's our product. Then you can have for the another one, if it attacks, this is below. So it attacks up. It attacks up above the plane of the carbocation. If it attacks below the plane of the carbocation, then you get this other product. Sa imuhang cyclohexane structure, one will be in the eggshell and the other will be in the equatorial position. Down equatorial and the other, for instance, up equatorial eggshell position. Question: what product would you expect from the mechanism of the iodine cyclohexane? Okay. I think you can answer this one. Iodocyclohexane, of course, you just have to write the iodocyclohexane, cyclohexane iodine, and then given as a reactant in practice 6.8. So the reactant. And then, of course, your reagent is methanol. So you can do this one 6.9. Now that we have an understanding of the mechanisms of SN2 and SN reactions, our next task is to explain why chloromethane reacts by an SN2 mechanism and tert-butyl by an SN1 mechanism. So I would also like to know or predict which pathway, SN1 or SN2, would be followed by a reaction of an alkyl halide with a nucleophile under varying conditions. So there are different factors that affects the rates of SN1 reaction. So there are some alkyl halides now that would follow the SN1. There are certain alkyl halides, for instance, to follow SN2 reaction. So we will differentiate why would a substrate such as an alkyl halide would follow an SN1 reaction or an SN2 reaction. So how do we alter the reaction environment in such a way that we would favor the SN1 reaction or that we would favor the SN2 reaction? Or simply by looking at our nucleophile or our reagents, can we predict if the said reagents can follow SN1 or SN2 reaction? So we'll talk about the factors that affects the rates of SN1 and SN2 reactions. So the answer to this question can be found in the relative rates of the reactions. Okay, so if a given alkyl halide and a nucleophile reacts rapidly by an SN2 mechanism, but slowly by an SN1 mechanism under a given set of conditions, so unsa may iyang i-follow, of course, since fast siya with SN2, then you expect that the alkyl halide at a certain nucleophile will follow the SN2 pathway. So this is different to the rate limiting reaction. We're just simply choosing which of the two types of nucleophilic substitution will be followed by a certain alkyl halide as our substrate. So kung asay paspas, asa siya paspas nga mo react, paspas siya mo react by an SN1 mechanism or SN2 mechanism kaysa sa SN1, then those alkyl halide and nucleophile will certainly follow the SN2 pathway. So on the other hand, if nucleophile may react very slowly by an SN2, but react rapidly with an SN1. So kung SN1 siya mas paspas mo react, okay, it will certainly follow the SN1 pathway. So there are different factors that affects the relative rates of SN1 and SN2 reactions. So first one is the structure of the substrate. Okay, if you remember, in SN1 reaction, to follow the SN1 reaction, we always first have to obtain the carbocation. And we've learned that the formation of the carbocation, the 3-degree carbocation is the most stable one than the 1-degree or the methyl. So it will give us an idea that whenever you have an alkyl with a 3-degree structure, 3-degree alkyl, it most probably follow the SN1 reaction compared with the SN2. We'll review on unsapoy substrate. You can review on the structure of the substrate for the SN2 reaction. Another factor that will affect on the rates of the reactions for SN1 and SN2 is the concentration and reactivity of the nucleophile. For example, in SN2 reactions only, the concentration of the nucleophile is very important. Third one is the effect of the solvent. Or is it the solvent would have in any way effect on the reactions on the pathway? It's SN1, SN2, and the fourth one, of course, is the nature of the living group. So for SN2 reactions, remember that the SN2 reaction is concerted reaction. You remember that when the nucleophile will attack the substrate, no, and it's concerted, and there is a living group, no, it will attack in such a way nga walay maghinder sa iya how it attacks the positive center. So in the SN2 reaction, the substrate that has only methyl, primary, secondary, tertiary the most stable one or the most preferred one in SN2 reaction is the one with not so much alkyl groups attached to your carbon atom having the living group. Okay? So baliktad siya with SN1 reaction because in the SN1 reaction, di ba, the more stable the carbocation having a more alkyl groups, the more it will follow the SN1 reaction. So baliktad siya. So for an alkyl group with only methyl and primary, it will always follow the SN2 reactions. So for example, here, some relative rates of reaction of alkyl halides and SN2 reactions. For example, let's compare methyl CH3X like at halide. Let's say just a halide. In a 1 degree, CH3, CH2, you have your carbon bonded to your halide, and you have another CH3. The relative rates of the SN2 reaction for methyl only is very, very large, 30, no, 30, while the 1 degree is 1 lang, no, and 2 degree is 0.03. Neopentyl, like you have your CH3, CH2, it's 0.001, particularly for 3 degrees, almost there is no reaction that happens. No. In fact, this already neopentyl on 2 degrees already also very, very slow reaction. So since the reaction is fast with only methyl and 1 degree, so in the SN2 reaction, it's more preferred with methyl and primary, no, as compared to the others. So this is actually your neopentyl. Why is that in the neopentyl? It's almost zero kind of reaction. It's a neopentyl halide. The neopentals, you have your halide attached to carbon, of course, and you have your CH3, your CH2. Remember, when your nucleophile attacks your carbon here and the leaving group leaves, no, it will attack from the backside. Now, if it attacks from the backside, but there is an alkyl group here, which is very, very bulky, then it will hinder the nucleophile to attack your partially positive carbon. And because of that, there is this factor as a steric effect, no, and steric hindrance. So what is a steric effect? It is an effect on the relative rates caused by the space filling properties of those parts of the molecule attached or near the reacting site. So it's steric effect. So because of this bulky groups, no, mas hinay ang rates because of the space filling properties of those molecules. So hinay, it will cause steric effect. Hinay ang pag-atake of the nucleophile during the backside attack to form a bond. Another one is steric hindrance. Steric hindrance is when the spatial arrangement of the group of atoms or near reacting site of the molecule hinders or retards the reaction. So it will hinder because of the presence of these bulky groups here. It hinders actually the attack of the nucleophile backside. So this is the front and this is the back. Now this is your living group. Of course, the nucleophile will not attack close to the living group in an SN2 reaction. Asa man siya mo-atake, it will attack sa likod, no, backside attack. And then the living group leaves, diba? That is the mechanism of the SN2 reaction. But when there is this presence of a bulky group, like this in the neopentyl halide, even if the nucleophile would want to attack this partially positive carbon center rather, no carbocation here, when it attacks this carbon, no, so it is being hindered by this bulky group, and this is what you call as steric hindrance. And you noticed here that the relative rates of the reaction to form during the nucleophilic substitution, having your neopentyl halide as your reactants is very, very slow. Similar also with alkyl, 3-degree alkyl halide. You know, there is this bulky group that will hinder the nucleophile to attack from the backside attack. So whenever you have, again, bulky groups, bulky groups attached to your carbon bearing the living group, it will always hinder the SN2 reaction. That's why in the SN2 reaction, mas taas ang rates of the reaction, mas pas-pas when you have only your methyl groups attached to your halide, then you have your 1 degree alkyl halides, and so on. Okay, so basically, it's only possible with methyl and primary, and very, very slow with the 2 degree alkyl halide. Okay, so here is an illustration of how would the space be seen for the alkyl groups present in your Okay, so this is an illustration of how your methyl looks like, no, when it attacks, or when the nucleophile attacks the alkyl halide, no, if there's only a methyl, so you notice here you have only CH3H3. And of course, in an SN2 reaction, SN2, emphasize the SN2, it always attacks from the backside because the reaction is concerted. When the nucleophile attacks, that's also the time when the leaving group leaves your substrate. So it happens in a concerted manner, simultaneous manner. Okay, so pag wala kayo bulky groups, then the reaction will be very fast. Like if we substitute hydrogen here with a methyl group, so that's a 1 degree alkyl halide or 1 degree substrate here. So there is this bulky group, but somehow the nucleophile can still find its way to attack from the back to this partially positive carbon here, and then your leaving group X leaves. If we increase the number of bulky groups to your partially positive carbon, attach your partially positive carbon like this one, so somehow mahinder gihapon si nucleophile, but somehow it managed pa na by 0.03 rates of the reaction. But if you have a neopentyl, or if you have a large bulky groups like 3 degree bulky groups here, tulo ka bulky groups, no, basically the nucleophile is hindered when it attacks from the back to this partially positive carbon. That's so therefore because it cannot attack, of course, the halides here can also not leave, and this is what we call a steric hindrance. So the presence of the alkyl groups hinders the reaction, the attack of the nucleophile by ang partially positive carbon center. Okay, next slide. Did siya move? Okay, so any questions? For the substrate, SN2 reaction favors methyl and primary halides. For SN1 reaction, the primary factor that determines the reactivity of the organic substrates in the SN reaction is the relative stability of the carbocation. So if you remember in the SN1 reaction, no, it first formed the carbocation, and you remember that the stability of the carbocation is much more stable when it is tertiary and then secondary or 2 degree. Okay, so you look at the structure of your alkyl halide and ask yourself what kind of carbocation will be formed when the leaving group leaves. So again, in the SN1 reaction, it favors the tertiary carbocation or 3 degree carbocation. Okay. So have time. We still have 5 minutes. So of the simple alkyl halides that we have studied, this means that for all practical purposes in the SN1 reaction, only tertiary halides reacts by the SN1 reaction. So 3 degree, of course 2 degree somehow, pero basically or for practicality purposes, only 3 degree reacts by the SN1 reaction. So it should be 3 degree, then 2 degree, 1 degree, and then methyl. But for practicality, it's only 3 degree that actually occurs in the SN1 reaction. At least for the SN2, you have the methyl groups 1 degree, then 2 degree. But for SN1, you only have 3 degree reactions. If you have an alkyl halide that would follow the substitution reaction, it's a 3 degree. Basically, it will not follow the SN2. Nga naman, the nucleophile cannot attack because of the bulky group present sa 3 degree. So, ng 3 degree, parehas ani, no? Parehas aning 3 degree. 3 degree, dili siya mahitabo sa SN2. Pero pag SN1, kaning 3 degree, kay mo leave mandaan si halide to form your carbocation, then it's easy. Then the carbocation can easily be stabilized by this alkyl groups. Okay? Question, rank the following alkyl bromides in order of decreasing reactivity from fastest to slowest of a substrate in the SN2 reaction. Okay, so which one would be fastest? A, B, C, D, in this reaction here. If this alkyl halides would follow the SN2 mechanism or SN2 pathway, asa may mas paspas. Which of this following substrate would be fastest to undergo the SN2 mechanism? Letter A, B, C, D. Is it all?
A.
SN2 reaction, it is SN2. Remember, SN2, it's a concerted. It is concerted. It's simultaneous, no? So it favors letter or 1 degree. It's my 1 degree din ha. So letter A, it's a 1 degree. Kinsa pa? A, sunod C. So A and B, they're both 1 degree, right?
Yeah.
A, but A and B will follow A. Next is
B.
D. Next is
B.
D. Next is so it's a 2 degree, and then bromine here, carbon here is bonded to 3 R groups, so it's a 3 degree. Carbon here is bonded to 1 R groups, also a 1 here, but you have a bulky group here, so between A and B, this is the most. A would be the fastest compared to B. So A, then B, then next is D. It's a 2 degree. Then last is letter C, of course. So C is, because C, it's a, what is the degree of the alkyl halide? It's a 3 degree, no? Okay, so very good. So here for C, basically it will not follow the SN2 pathway. It will simply follow, since it's a 3 degree, it will follow the SN1 pathway. You always have to remember this SN1 and SN2 pathway, no? Because of course, in the future, it will always come out sa inyong board exam. Okay, so have 5 minutes. So let's go back to the SN1 reaction. Basically, as I've mentioned, only tertiary. It should be tertiary 2 degree in the basis of the stability of the carbocation, but basically for practical purposes, only the 3 degree alkyl halides reacts by an SN1 reaction. And then later we'll see that the allylic halides and benzylic halides can also react by SN1 mechanism. And why is that? The carbocation that's being formed when you have the allylic halides and benzylic halides are being stabilized by resonance. So we'll look at the structure in, I think this will happen in chapters 13 of atong reference book, which is Solomon's. Again, the tertiary carbocation are being stabilized by sigma bonds at 3 adjacent carbon atoms by hyperconjugation. No, the sp3 and the p unhybridized orbital of the carbocation will have a partial sideways overlap or partial overlap. No, and that's hyperconjugation. Secondary and primary carbocations, of course, have less stabilization by hyperconjugation, and particularly the methyl. So as mentioned, only tertiary carbocations would have practical undergo SN1 reactions for practical purposes. If the reaction is fast, if we have the secondary and primary or methyl carboxylate ion, the reaction is very, very slow. Mura ra kagulay reaction na hita po, basically. So of course, we choose the pathway when we do the reactions. The reaction occurs very, very fast. And you always have to remember the formation of a relatively stable carbocation, like when you have the substrate, you have the R group with the leaving group here. Whenever you produce your carbocation, whatever ways, whatever factors to stabilize your carbocation, such as your tertiary carbocation, then it will be reasonable to have the SN1 reaction pathway. So let's have a question. Which of the following alkyl halides most likely to undergo substitution by SN1 mechanism? ABC.
C.
Okay, unsa ganitong pathway, we always follow the unsa ganitong substrate dapat ang the most stable carbocation when it forms a carbocation. So asa man sa ila, ang the most stable carbocation should be at 3 degree. Of course, kung alkyl halides pala na siya, 3 degree dapat siya. So asa man din ha, ABC. Letter, kinsa ito nag-storya? Letter, isa yung C. C daw. Okay, it's letter C. Next is letter C is 3 degree. No, anong C man? Because it's a 3 degree. Alkyl halides, when it forms a carbocation, it also forms a 3 degree carbocation, and it is a more stable carbocation. Therefore, it will be the fastest one to follow the SN1 mechanism. Next one is letter
B.
Letter 2 degree, so it's letter B. Next one is the 1 degree. They're very slow, but anyways, it's letter A. So C, D, A. Fastest to, isa na the question. So wala ko yung answer. Okay. So the answer here is letter C, fastest na natin. So let's see, before we end, there is a pickle as the Hammond-Leffler postulate, Hammond-Leffler postulate. So if you review on the free energy diagrams that accompany the mechanism of the SN reactions of the SN1 reaction of tert-butyl chloride and water, you will see that step 1, the ionization of the leaving group to form the carbocation is uphill in terms of the free energy. What do I mean by that? It's uphill, it means it's positive. So it's also in this term that we can apply the delta H is also positive. So according to Hammond-Leffler postulate, the transition structure for a step that is uphill in energy should show a strong resemblance